Students, we are going to consider vibration of continuous systems in this third module, and the system that we are going to consider in this lecture is a string. So we are going to consider vibration of a string which is under tension, and actually we are going to consider transverse vibrations. Okay, so assume that there is a string which is fixed at two edges. Okay, and under certain initial condition, let's say if you give certain initial condition to it, and then it performs vibration in the transverse direction, a direction which is transverse to its length. Okay, so this is the length direction, transverse to this direction the string is performing vibrations, and we are going to first of all derive the equation of motion for this vibration, and then we are going to see how can we solve this system. Okay, so to start with, what we'll be doing is, let's assume that the string is in vibratory motion, which is this motion. Okay, so this is the instance that I'm going to consider. Okay, this is at some intermediate location, and let me consider a small portion of the string, okay, which is this one. Okay, so this is the portion that I am considering, this portion, okay, which is a very small portion. So I'll be considering that it is, this distance is dx, okay, delta x or dx, which is very small. Okay, so for this small distance dx, so how exactly string is going to behave? So let me take the string out from here. Okay, magnify it and draw it, so it will look something like this, right? Let me draw my coordinate system over here. Let this be called as x, let this be equal to y. Now this y is the coordinate that is going to change for each particle on the string with respect to x as well as with respect to time. So that is what is this continuous systems, which this transverse displacement, okay, which we are accounting by y. Okay, we'll be saying that this y is equal to how much it has got displaced from its mean position. Okay, so we'll be measuring y with respect to mean position. So this is the reference. So with respect to that reference, so how much amount of transverse deflection that string element has seen, that is what is we are representing by y. X is its location along its length. Okay, and this y is going to change for any particular time along x, and at any particular x, let's say if you stand, so let's say if you are standing over here, okay, this is the point which is fixed. If you are standing over here and if you are observing it for some good amount of time, then you will be able to see that vibrations at that location. So that which essentially means that that particular string element which is at that location is changing its displacement with respect to mean position as time progresses on. So you get to see change in y along two domains or two directions. One direction is space direction, space dimension, which is x, and the other dimension is the time dimension, which is t. So y is changing with respect to x as well as with respect to t. So which essentially means that y is going to be a function of two variables which are x and t. Okay, so as of now we are going to consider for a certain time t what is happening. Okay, so let's say that as if you have taken a snapshot, so time domain is freezed and you are seeing this curvature of this particular uh, string. So this is how string is going to look like at that particular time. Okay, so you have fixed both ends of the string over here, and this is the profile that string has taken, and you are looking at that profile and you are taking out small portion of that string, okay, and writing down force balance on that. So that is what is we are doing right now, and we are saying that the string is always under tension. Okay, and I am going to make one more approximation over here, is that this y is very small, okay, and hence there is no change in t. Okay, it's not vibrating in a very large amplitude sense, so which essentially means that there is not going to be much difference in the tension of the string. Okay, so because of its motion along y direction, there is not going to be any change in t. So this is what is the approximation. Actually, in actual practice it won't happen. Tension is also going to be a function of y, but we are assuming, in order to make our life easy and in order to go ahead in formulating this differential equation, this is one assumption that we are making. Obviously you can get rid of that assumption and then you will get a slightly complicated differential equation, but we are not going to look at that. Okay, so we are saying that T, which is tension, is constant, okay, along length. Okay, it's not varying along x direction. Okay, so under all these approximations, so we are trying to draw free body diagram of it. Okay, so let me say that this is the tension, okay, this is the force which is applied by adjacent string. So what we are doing is we are taking out this much amount of string outside. So if you take it out, if you will have to cut it over here, and the moment you cut it over here, you will be able to see forces which are acted upon this by adjacent string portions which you have removed. Okay, so we are considering that these are those two forces. So one force component I have drawn over here, which is this T, and I'll be drawing a similar component over here, which is again will be T. Okay, we are assuming that this T is not changing, value of this T is not changing. Okay, it remains constant throughout x direction. However, what is changing is this theta, right? As you move along x direction, what is changing is theta. This is theta over here, and what will be angle over here? It will be theta, that is what you have measured over here, plus some increment because you have marched along x-axis. Okay, so this theta which you are going to observe over here, this angle theta dash, whatever you call it, okay, that will be what you have seen over here at this location, at this reference location, plus some additional angle that is going to come because you have marched along x-axis, and that I'll be writing it as del theta by del x times dx. Okay, because you have marched dx units along x direction, okay, you are going to see this much amount of additional theta. So this is variation of theta with respect to x. Okay, so this is variation of theta with respect to x times dx. That is going to give you how much additional theta is going to come over here and get added to the previous value, which was this theta. Okay, so this is what is the angle. So let me draw it once again over here neatly. Okay, so this angle we refer to as theta plus this was del theta del x dx. Okay, so why I am considering partial derivative? Because this angle theta is going to change along x direction as well as along t direction. But right now we are freezing this time variable. Okay, we are assuming that we are taking a snap at certain time instance, and what is happening at that time instance is something of interest to us. Okay, so in that sense, this is what is going to be the value of theta at this location. Okay, now let me draw force which is acting at this end, which is again T. This is force T, and its angle, either you call this angle theta or you call this angle theta, it's going to be the same one. Okay, so this angle is theta, so that theta is going to change as you march along this, okay, x-axis. Okay, so now let me try to write down what are unbalanced forces which are acting onto it. Those are equal to T sine of theta plus dabba theta dabba x dx. Okay, so what is this? This is unbalanced force acting in vertical direction. I'm going to write down force balance only in vertical direction, because I am kind of considering only vibrations in transverse direction. Okay, I'm not going to consider those vibrations which are along the length direction of that string. Okay, so that is something that I'm not going to consider over here. So I'm considering sine component of it. Cos component will tell you how much amount of force is over here, and sine component will tell you that how much amount of force is acting along y direction because of this t, and which is equal to t sine of theta plus dabba theta by dabba x into dx. Okay, so this minus t times sine of theta is the total force which is acting onto it in y direction. Okay, and we can write down our force equilibrium, okay, considering acceleration term as well, which comes out to be like this. I'll write down the first term, force term here, over here, then this is the second force term which is on the other side, which is on this side. Okay, and this needs to be equal to mass times acceleration, which comes out to be like this. There has to be a change. Okay, it needs to have ds del square y by del t square. This is acceleration term and this is mass. So this is total inertial term which we have written over here. So how we have calculated mass? We are assuming that rho is mass density multiplied by A. A is the area. We are considering that area of the string is not changing with x. Okay, it remains constant, and to that we are multiplying by length of the string. Okay, length of the string portion that we are considering, and that length is actually this arc length, which is equal to ds. Okay, now when this delta x is very small, okay, delta x being very small than 1, okay, it's like infinitesimally small. So in that sense you can approximate this ds by dx, and hence you can write down equation whatever that we have written over here in the simplified manner like this. Yeah, I'm going to make one more assumption over here. The assumption is that actually we have made that assumption that we are having very small transverse vibrations, which essentially means that y is going to be very small, and hence you will be able to see that theta is not going to be very large. Okay, you can't see big thetas like this. Okay, so you won't be able to see something like this. Okay, so such kind of theta. Okay, so it won't happen. So from that perspective, theta will always be small, which essentially means that since theta is very small, you can approximate sine of theta by theta itself. Value of sine of theta will come out to be approximately equal to theta, and then we are going to put this approximation and this approximation in our earlier equation, and if you do so, what you get is t times sine won't be there now. Here you are having theta plus dabba theta by dabba x into dx minus t times theta. It was sine theta, now it has turned into theta only. Okay, that is equal to rho times a times dA times del square y by del t square. Yeah, I have forgotten one thing. The thing is that we should have a also mentioned over here. This a is actually area, and I have forgotten that thing. So we should have area term coming over here. Okay, because this is tension, which is this. In order to get the force, you need to multiply by a. Okay, so so in that sense, what we get finally is, let's try to simplify this. So t a theta coming from here and this t a theta coming from this side, they'll go away, and you will be left with this quantity, which is t times a times dabba theta by dabba x dx, that is equal to rho a. This is ds, which needs to be replaced by this ds will be replaced by dx, as this dx is very small, so it is dx times del square y by del t square. Okay, now this a will also go and this dx will also go, and what you are left with is del theta by del x is equal to rho by t into del square y by del t square. Now this is what is going to so what this equation is telling you is that, so what is this variation of theta with respect to x? Okay, in order to have force equilibrium, variation of theta with respect to x should be such that it is scalar multiple of its acceleration profile. Okay, so whatever is the acceleration profile, it is scalar multiple of that acceleration profile, and what is that multiplier? Multiplier is equal to rho by t. Okay, now we are going to go even further, and we are going to replace this theta in terms of y. Okay, which is transverse displacement, that you can simply do by looking at the geometry. Okay, if you look at the geometry, you will be able to see to it that theta is nothing but del y by del x. Okay, so if you put that approximation over here, that's not an approximation, that is coming from geometry. So if you put that expression over here, then you get to see this equation dabba by dabba x or del by del x of del y by del x, that is equal to rho by t times del square y by del t square. Okay, which essentially means that del square y by del x square is equal to rho by t times del square y by del t square. Okay, this is what is our final equation, okay, which is also called as a standard wave equation, and it tells us relationship between variation of y along x and t, and that relationship is written like this. Okay, where c square is a constant, okay, which is t by rho, okay, or c is equal to square root of t by rho, and the c, why we are writing it down in this fashion? Because the c represents velocity of the wave which is traveling along the screen, this string. However, we are not going into wave, okay, but it is generally written in this fashion, and it is called as a wave equation. Equation for wave and vibration is same. However, there is subtle difference between these two things, and we are not going to talk about that now. Okay, we are going to consider only vibrations, and from that perspective we are not going to go into very details of those wave equations, I mean in of waves, and we are going to consider this as vibration of equation governing vibration of the string. Okay, along with this equation you also need two initial conditions, and those two initial conditions are not the only conditions which are required. Something else is also required. These two initial conditions are because you have this second order dependence on time, but you also have second order dependence on space over here, so you will also need two conditions, okay, along space direction. So that is called as a boundary condition. So you have two boundary conditions, okay, and two initial conditions, and therefore this problem comes out to be initial boundary value problem. So you have initial value specified, you also have boundary value specified. So let's have a look at those conditions. So this is the string that we were talking about, and this was the profile of the string, okay, and we said that this is what is y, with respect to mean position, how much it has shifted. Okay, and now boundary conditions will be referring to these points, okay, which are 2 points at left end and right end. Okay, what we know is that y at x is equal to 0, and for all time that should be equal to 0. Similarly, y at x is equal to L, and for all time it should be equal to 0. These are two boundary conditions, and we also have two initial conditions, which are y for all x values at time t equal to 0 should be certain function in x. So you are giving certain distribution of y to start with. Okay, so let's say this is what is the initial condition that you are given. So what is that? That is function of x. Okay, similarly you will also be providing velocity. So I'll be calling it as del y by del t, or we represent that as y dot. This evaluated at all x values and for time t equal to 0. Okay, so we'll be calling it as y dot at x and all time 0, that should be equal to another function f of x. Okay, so you are providing variation of velocity along length of the string, which is this function. Okay, so this function is going to tell you how velocity is going to vary from this end to that end. Okay, this function is going to tell you how displacement is going to vary from this end to this end. Okay, so these are two boundary conditions. Sorry, these are two initial conditions. So these two initial conditions along with these two boundary conditions, you have in all 4 conditions with you, of which 2 are initial conditions and 2 are boundary conditions, and this is what is a typical initial boundary value problem. Now we have done formulating this initial boundary value problem. Now we are going to see how can we solve this equation. Okay, so this is one single equation, okay, which we are getting for a continuous system. This is also called as a distributed mass system because we have mass distributed. That's what is coming over here. So inertial force, if you see, this inertial force is a distributed force. Okay, and since inertial force is a distributed force, you are going to see this as distributed inertial force coming because of this this rho, which is this density is distributed at all points along the string. Okay, so we'll be stopping over here on this front, and we are going to see how we can solve this equation in the next class.